Yeah, so double integrals, right? So there's an exercise left from Tuesday. So let me just remind you of the exercise. So we had this double integral. So we have to, I think we had to evaluate. Oh, I'm gonna just zoom out. Yeah. Okay, so we have to evaluate the double integral over the region D, okay, of the function f. So where D is, so D I think was the following triangle. So here's your x-axis, your y-axis. All right, so 1, 2, let's say here's 3, here's 1. So this is the point actually 3, 1. And so we have this triangle here. So our region D is the interior of the triangle, of course. That's our region D, right? So we have to evaluate this triangle, this integral using two different ways, right? We said we have to use using two different ways, right? So, so what we have to do, guys, of course, we have to describe, this region D. So actually, it turns out this region D is of type 1 and also of type 2. So if you want to describe D as a type 1, so here's your D. So first, you try to fix the x coordinate. So x coordinate, the variable x would be between the variable x would be between 0 and 3, right? So x is between 0 and 3, right? So we have a point here at 0. So x equal to 0 here. This is x equal to 0. And this is x equal to 3, right? And here's x equal to 3, right? And now, so if you want to connect the point x equal to 0, where x is the origin to the segment x equal to 3, then so here you're going to have this first function. Here it's actually the function y equals to 0, right? And here, so the equation of this line is, of course, so this is, so this line here, it passes through the 0, 0, the point 0, 0, and the point 3, 1. So the equation of this line actually is y equals to x over 3, right? Because when x is 3, y is equal to 1. And if x is 0, y is 0. Anyway, so then your y is between these two functions, y equal to 0 and y equals to x over 3. All right. So, so my x is between two constants. So this is a type 1. This is a type 1. This is a type 1 description of the region D. And now you can evaluate your integral. So your double integral over D of x. So in case of type 1, your x is between two constant and your y between two functions of x. So you integrate first with respect to y, right? And then with respect to x. Okay, so because, again, it's because your x is between two constant. All right, and y is between two functions. So first you integrate with respect to y, and then with respect to x. And here's your function. So our function here is x. right? This is my function f of xy. So here we're going to put x, the function x. So y, we said it's between 0 and x over 3. So here's my 0, here's my x over 3, and x is between the two constant, 0 and 3. So my x is between 0 and 3. Right. Yeah, so we know how to, of course, how to compute the double integral first. So here we have to integrate with respect to y. So we consider, x, we integrate with respect to y, and we consider x as a constant. So here, so we integrate with respect to y first, right? Assuming x to be constant, right? Assuming x to be constant. All right, so that will be equal to, so we keep the 0, 3, the dx, the integral with respect to x. So integral of x with respect to y, so x is constant. So an integral of a constant, that will be the constant times the variable. So it's the constant, the variable here, it's of course y. So it's x times y, right? Evaluate between 0 and x over 3. Now you substitute y, right? Because we integrated with respect to y, so we substitute y by x over 3, and then by 0, right? So here's my integral with respect to x. So x times, so y is x over 3 minus, and then y is equal to 0, so it's x times 0. So this is, of course, this is just 0. Right, so it's just the integral of x squared over 3, right? So this is integral with respect to x of x squared over 3, which is integral of x squared. It's x cubed over 3, so it's x cubed over 3, and there's this constant 3 in the denominator, so times the constant 3 here in the denominator. So it's just x cubed over 9, right? Evaluated between 0 and 3. Right, and so if you substitute x by 3 and then by 0, we're gonna have 27 over 9. That will be equal to 3, and then minus 0, so that the answer would be 3. Okay. So this is the first way to compute this integral. Any question, guys? Now, if you try to fix y first, so now I'm going to describe D as a region of elementary region of type 2. So as type 2. So then D can be described as, again, so we have this triangle, this is a point 0, 0. This is, here's 3, 0, and here is 3, 1, right? So first, this is, of course, x-axis, this is y-axis. So first you fix your y. So the variable y is between, as you can see here, this is y equal to 0. And here, y is equal to 3, right? So your variable y, if you fix y first, then the variable y is between 0 and 3. Okay. So again, you have this point here on the top, this is a vertex, and you have this segment in the bottom, right? Now we're gonna connect the segment to the point. So I'm gonna use the function here, right? This is a function, let's call this function g of y, right? And here, another function, h of y. So this function g of y, well, I mean, this line, the equation of this line, we said it's y equal to x over 3, okay? But now we are looking for a function of y, right? So we have to solve for x. So this is equal to x, which is x is 3 times y, right? So this is x is equal to 3 times y. So here it's 3 times y. And here h of y, this is just your x. And here the equation of this, f of this vertical line is x equal to 3, right? This is the point, here's the point 3 is 0. So the equation of this line is just x equal to 3, right? So so then your x is between, so then x, so y is between 0 and 3, and then x is between 3y, okay, and 3. Okay. So when you evaluate your integral over d of the function x, right? So now my y is between two constants, right? And my x is between two functions of y. So then we have to integrate first with respect to x, right? So first we integrate with respect to x. So here, first we have dx and then dy. Okay. Again, it's because your x is between two functions of y and y is between two constants. So you integrate first with respect to x. Here inside this, here my function f, again, it's just x, right? So we said x is between 3y and 3. So here's 3y and here's 3. And my y is between, sorry, this is 1 here. I said 3. This is 1, of course. This is 1 here, right? This is the point 3, 1. So the y coordinate is 1. So this is 1, sorry. Okay. So this is just 0 and 1. Right. So first we integrate with respect to x. So here we integrate with respect to x. Right. Assuming y as a constant. Okay. So integral of x, of course, it's just x squared. So this is, well, first we have this integral with respect to y, so I'm going to keep it. We integrate x, so with respect to x, it's just x squared over 2, evaluated between 3y and 3. Right. So then, so you substitute x with 3 first. So this is an integral from 0 to 1. So 3 first. So we're going to have 3 squared over 2 minus, and then you substitute x with 3y. So that's 3y squared over 2, right? Dy. Okay. So it's just, it's 9 over 2. So this is integral 0, 1, 9 over 2 minus 9 over 2, y squared, dy. You integrate now with respect to y, right? So integral of 9 or 9 halves, or 9 over 2 with respect to y is just constant. So that will be 9 over 2 y minus, and then you integrate y squared. So that's 9 over 2, my constant. Integral of y squared, it's with respect to y, it's y cubed over 3, right? And this is evaluated between 0 and 1, right? So you will substitute y by 1 first, and then by 0. So of course, when you substitute y by 0, it's going to be just 0. So if you substitute y by 1, so we're going to have 9 halves minus 9 halves here times 1 cube over 3, 1/3. Right, so it's just 9 halves minus 9 over 6. And then that will be actually equal to, we can reduce the 9 over 6. That will be 3 over 2. So that's actually 6/2, which is of course equal to 3. And as expected, of course, we get the same answer as the first way. So in the first way, we described D as a type 1, right? And we got the answer was 3. And the same thing, when you describe D as a type 2, you get the same answer. You get 3. Any question, guys, about this exercise? So anyway, so I'm just I'm doing this exercise because, just to show you that it doesn't really matter which how you describe your region D as a type 1 or as a type 2, you're gonna get the same answer, right? Anyway, so now next, well, so you may ask, why do we bother to have so many ways to integrate our function? Well, sometimes it's very useful, to change, the order of integration. So I'm going to show you with an example. So sometimes it's useful to describe, D as type 2 instead of type 1, or type 1 instead of type 2, right? So for example, so the remark here is that sometimes, so having different ways to integrate is sometimes useful, right? So having different ways to integrate is sometimes useful. All right. So, for example, again, I'm going to use the same region D, the triangle. So my D is, again, the same. It's the same region. So it's this triangle. Again, 0, 0 here. 1, 2, 3. 3, 0 here. And then let's say this is x-axis, of course, y-axis, and this is 1 here. So this is the point. So this is the point 31, right? So again, it's the same region, right? Now, let's say you want to evaluate the double integral of of the function e to the power x squared, all right, dx dy, okay, over this region D, right? So this is just so if you integrate first with respect to x and then with respect to y, so you need to describe D as type 2. Okay, so this is we said in this case we're going to have so dx here. So your x is between, we said type 2, x, it would be between 3y and 3, and y between 0 and 1. Okay. So now my question for you guys. Of course, here this double integral, we have to integrate first with respect to x, right? So my question is, what will be the integral of e to the x squared with respect to x? What's the integral? What's the antiderivative of e to the x squared?
E to the x squared. Sorry. To x.
Nope.
No, 2.
Integral of e to the x is e to the x, right? Plus a constant. It's e to the x. But this is, so be careful here. It's e to the x squared,
yeah,
right? So
okay, we need to substitute x squared with you.
Yeah, but if you wanna try to integrate by using substitution, then you're gonna need the derivative of x squared in front of the exponential. You're gonna need at least x, right?
Yeah, right.
if you use a substitution, then yes, then this probably you're gonna need you're gonna divide by 2, so this would be e to the x squared over 2 plus constant, right? Dx here. All right, so if you use a substitution, then you're gonna need x in front of the e to the x squared. But here there's a problem. There's no x in front of e to the x squared. All right. So now, so my claim is that, in fact, the antiderivative or the integral of e to the x squared, it cannot be expressed as a combination of elementary functions, actually. You cannot express the integral of e to the x squared using elementary functions. What do I mean by elementary functions? I mean like, exponential or logarithm or powers of x or trig functions, etc. So all the functions, they're just elementary functions. Okay. So my claim is that, and actually, to compute the antiderivative of this e to the x squared, you're going to need a power series. You can try to approximate the antiderivative of e to the x squared, but you cannot express the integral of e to the x squared using just elementary functions. So my claim is that there's a problem here because the integral of e to the x squared, it cannot be expressed as a combination of elementary functions.
Yeah, right. But if we change the order, it will be exactly for substitution, and it will be easy.
Yep, absolutely. And that's why this changing the order of integration sometimes is useful. Yeah, absolutely, a good point. So so this cannot be expressed as combination of elementary functions. Actually, the best thing you can do here is to use power series to approximate this elementary functions. So what we can do here, just for your information, of course, you can try to use a power series to approximate this integral of e to the x squared. I don't know if you, I guess, well, in calculus, I guess you guys, you have seen this power series and probably and Taylor series, right? And so you know that e to the x can be expressed as a power series. That would be the sum of x to the power n over n factorial. So then e to the x squared would be just x to the power sum of x to the power 2n over n factorial. Anyway, so all I'm saying is that this antiderivative of x squared, it can be approximated using power series, but it cannot be expressed as a combination of elementary functions. So then the idea, as you said, so the idea would be now to change the order of integration. So now I'm going to describe D as type 1 instead of type 2. All right, so I'm going to, so here's my integral e to the x squared. I had this dx, dy. We said x is, between 3y and 3. Y between 0 and 1. So this is, we said this is type 1 here, type 1. So if you change the order of integration now, this is e to the x squared, now dy dx, right? So this is now type 2. Okay, so then we said, in the previous exercise, if type 2, we're going to have, so y between, sorry, this is I said type, this is a type. So this is type 1. Oops, come on. So this is, and this is type 2. So type 2 then, y would be, we said, where's y here? Where is it? So we said y would be between here. As you can see, so y would be between 0 and x over 3, and x between 0 and 3, right? Sorry, I got the right types. I don't know why I changed them here. Sorry, this is sometimes. So this is type 1. That's correct here. Type 2. Anyway, so so in this case, y would be between 0 and x over 3, and x between 0 and 3. Right? Now I have to integrate first with respect to y, right? So if you integrate with respect to y, well, you kind of solve your problem, because e to the x squared would be just a constant, right? So it's just like integrating a constant. So you integrate with constant with respect to y, that will be equal to the constant times y, right? So that will be equal to, so here's the 0, 3. Here's x dx. So you integrate this constant e to the x squared. That will be e to the x squared times y. Y between 0 and x over 3. Right? So you see, guys, why this change of order of integration is sometimes useful. It can solve your, sometimes you can solve easily your problem. So now you substitute y with x over 3, and then you substitute y by 0. Of course, you're going to get 0. So we're going to have just e to the x squared times x over 3. Now, you see, now I have an x in front of the e to the x squared, right? I have this x now, and that solves my problem, because now I can use substitution to integrate, right? So I'm going to use a substitution to integrate. Okay. So let's say u is equal to so what will be the substitution here, guys? Well,
x squared.
Yes, u is equal to x squared. I'm sorry. So yes, u is equal to x squared. So then du, so derivative of u, so du would be the derivative of x squared, which is 2x. Of course, you need the dx. Okay. So then, or in other words, this is just or you can just say, so in other words, this is, or if you prefer, this is, so the derivative of u with respect to x is du dx is equal to 2x. So then dx or du is equal to 2x dx. All right. You just you cross multiply. So x dx would be du over 2. So x dx would be du over 2. All right, so I have here, of course, I have this x dx here. That will be du over 2. So let's just substitute here. So that would be x dx would be du over 2. This is du over 2. e to the x squared, of course, x squared is u, so that's e to the u. So this is e to the u. All right. And there's a 3 here, this constant, don't forget this constant. So here's over 3, right? So that will be e to the u, integral of e to the u over 6 du, right? And what would be the integral? I mean, over 6 is just constant, so we don't worry about the constant. So integral of e to the u with respect to u, well, it's just like saying integral of e to the x with respect to x, it's just e to the x, so that would be e to the u. So this is equal to e to the u, right? But then over 6, of course, don't forget the constant. So, and then u is x squared, so this is just e to the x squared over 6. Okay. And so x, don't forget your x, the bounds of x is 3 and 0. So here we have 0 and 3, right? So when x is 3, you're going to have e 3 squared over 6 minus, and then you substitute x with 0. So that's e to the 0 over 6. So that would be equal to, final answer, so that would be e to the power 9 over 6 minus 1 over 6. Okay, so that's the final answer. Any question, guys? So you see how I solve this double integral when I change, so I had to change the order of integration, right, to solve this integral. All right, so let me give you like a similar problem. So, so here's an exercise. Okay, so evaluate. So please try to evaluate the following integrals, and you will see you have to change the order of integration. So first integral is, so let's say you have a double integral. It's 1 minus y squared to the power half, or let's say just it's a square root. I should use the square root here. It's the square root of 1 minus y squared. Okay, dy dx. And the bound, so here x is between 0 and 1, and y is between 0 and square root of 1 minus x squared. Okay. A second integral. So as you can see here in this first integral here, guys, so we have to integrate square root of 1 minus y squared with respect to y, right, first. But here there's a problem because it's not just 1 minus y squared, it's the square root of 1 minus y squared, right? So if you try to use a substitution here, then you would need like a y in front of your square root, right? If you want to use substitution, but there's no y here in front of the square root. So actually you need to change the order of integration to evaluate this integral. Number 2, again, double integral, 1, 2, 0, log of x. So here I'm going to have x minus 1 times 1 plus e, again, square root. So we're going to have, let's say, square root of 1 plus e to the 2y dy dx. Right? And again, because so in this second integral, you need to integrate first with respect to y, right? And then there's a problem here. It's because, well, because of the square root, you're going to have a problem. You're going to have trouble to integrate, right? That's why you're going to need to change the order of integration. Anyway, guys, so I'm going to give you, let's say, 5-10 minutes to think about this exercise. So in both cases, you're going to see if you try to use substitution, to integrate with respect to y, then you're going to have trouble with that because there will be some missing terms. All right, so then you need to change the order of integration as the previous example, right? Anyway, so I'm going to give you 5-10 minutes to think about this exercise. So this is kind of similar to the problem 4 in the homework. So in the problem 4 in the homework, you're gonna need to change the order of integration, okay? So this is similar to problem 4 in the homework. Zivola, you got 2/3 for the first one. Yeah, I think your answer is correct. Very good. Very good.
Okay.
Mm-hmm. So when you change the order of integration, guys, one of the problem is that you have to sketch your region D, so make sure you have the correct bounds for your integral. David, you got pi over 4 minus 1/3 for the first one, or for number 2, I guess, right? First one? Mm, pi over 4. Well, actually, I don't, I don't have the answer, but I don't think it's gonna be pi over 4 minus 1/3. But I will see. I mean, Vzivolod answer 2/3 makes more sense to me. But anyway, we'll see. Well, I mean, this is good. It means that the problem is not easy. It's not an easy one. I guess, David, you try to use polar coordinates. Anyways, for polar coordinates, I mean, we're gonna do the polar coordinates after the triple integral. So we're gonna change. We're gonna see how to change the variables to make integrals easier to compute. But I mean, in this case, yes, that's one way to to evaluate this integral. You can try to use the polar coordinates, but we see the polar coordinates after the triple integrals anyway. But the goal of this exercise is really just to change the order of integration, right? So again, guys, you have to sketch the region D. Make sure they have the correct bounds when you change the order of integration, right? Any guess for number 2? I think number 2 is not an easy one because the bounds, when you change the order of integration, the new bounds, I mean, you have really to sketch the region D. So you can see exactly what are the bounds, what will be the bounds when you change the order of integration. So for later, guys, I mean, for triple integrals, sometimes it's very hard to graph, functions in the three-dimensional space. So I'm gonna try like a new experience. I'm gonna use like there's a nice software. I'm gonna use it to graph, functions in of three variables. Um, well, I mean, double integrals when you're in dimension two, it's kind of it's not a big deal. I mean, if you want to graph functions, but in three dimension for triple integrals, that would be kind of not easy. So I'm gonna probably use like kind of like a software or something, so we can show you, the graph of functions in 3D. Um, that would be better. I mean, to visualize the graphs, right? Um, So, did anyone finish number two?
Not yet. I'm still trying to switch the order.
The order, yeah, yeah. It's not an easy one. So in the homework, guys, you have like four different problems. The first problem is just it's just the double integrals, and it should be easy to integrate. Problems two and three, you have to find the area of some region bounded by some graph of functions. I will remind you in a couple of minutes, but the area of any region would be the double integral of the function of the constant function one, right? Over your region, right? Um, and then there's a problem four, and the problem four, you have to change it again. It's kind of similar to this exercise, so you have to change the order of integration. And actually, I forgot to include. Remember, guys, I think we discussed this last week or on Tuesday. I'm not sure, but we at some point we discussed the case of when the region D is it's given by an annulus, right, bounded by two circles of radius 1 and radius 2, right? So your region D is like a ring shape region, right? So and we said, and I claimed that D, if you have an annulus, then annulus is not elementary region, right? But the idea would be to divide, that you can divide your annulus into like 4 elementary regions, right? Um, David, you got 0. I don't think it's gonna be 0 because actually it's I mean, my function log here, log of x, it's defined, so x is between 1 and 2, right? So log of x here is positive. So it should be the area of some reason, some region, right? So it should be positive number here. The answer should be some positive number. I think so, right? Well, well, there's this function. Your function is also positive. I mean, you have square root x minus 1, x minus 1, x is between 1 and 2. So everything here is positive. So the answer should be positive number, I think. But anyway, probably I should probably I should start solving number 1, and then we'll see for number 2, right? So let's start with number 1. So for number 1, we have this double integral 0 square root of 1 minus x squared, and then we have this square root of 1 minus y squared dy dx. So first remark is that if you try to integrate with respect to y, then you're going to have a problem, because so if you try to integrate square root of 1 minus y squared dy, right, then because of this square root, you have to try to use the substitution, right? So if you let's say if you try to use the substitution, and let's say you substitute y squared by u, for example, let's say u is y squared, right? Then du, du would be equal to 2y dy, right? But then there's a problem here, because we don't have the y dy. We only have dy, right? There's no y here, right? So we don't have the y in front of the square root, so actually we cannot use the substitution, right? So then there's a problem, and so we have to, as I said, we have to change the order of integration, right? So now I'm gonna change the order of integration, but before that, I'm gonna sketch my region D. So make sure that my bounds are, when I change the order of integration, I wanna make sure that my bounds are correct, right? So what's my region D in this exercise? Well, in this problem, well, I have my x. Here's my x. X is between 0 and 1. All right. And then my y is between 0. So this is a type 1 region. So y is between 0 and square root of 1 minus x squared. All right. So let's try to sketch this region D. So here's my x-axis, y-axis. So this is 1 here, this is 1. So my x is between 0 and 1. So when x is equal to 0, so here x is equal to 0, and here x equal to 1. X equal to 0 is, of course, just the y-axis. X equal to 0, and x equal to 1, that would be this vertical line here. This is x equal to 1. So I'm saying my x is between 0 and 1, so so that corresponds to this region here. That's the region where x is between 0 and 1, right? Now next, y is larger than 0, so here we have y equals to 0. Okay, so y equals to 0, of course, is just the x-axis. So here's y equals to 0. All right. And then y is less than square root of 1 minus x squared. Or in other words, that will be the graph of the function y equals to square root of 1 minus x squared, right? So we need the points below the graph of the function square root of 1 minus x squared, right? And I mean, square root of 1 minus x squared, I mean, if you use a square here, then your y squared would be 1 minus x squared, and so y squared plus x squared is equal to 1. So this is just the circle of radius 1, right? So you have this circle. Of course, here y is equal to positive square root of 1 minus x squared, right? So y should be, your y should be a positive. So it's just, so it's going to be just the upper circle here, this one here, right? So this is where y is equal to positive square root of 1 minus x squared, right? Because the y coordinate is positive there. So then what will be my region D? Well, it will be this. Y is larger than 0, so it's going to be above the x-axis and below my circle, right? So my region D would be this one here. The intersection of all these regions would be this one here. So this is my region D. All right. Okay. Now I want to change the order of integration, right? So now when you change the order of integration, so we're gonna start with a y. So here again, we started with x. We said x is between the two constants 0 and 1, and then y is between these two functions 0 and square root of 1 minus square root of 1 minus x squared, right? Now I'm gonna change the order of integration. So then first my y would be so again, here's my region D, sorry. So my y would be between, well, I'm going to use a different color. So let's say I'm going to use the yellow. So y for this region D, so if you start with y between two constants, then that will be y equal to 0. That's my first constant. And the second constant would be this one here. This is y equals to 1, right? So because my region D is between these two horizontal lines, right? So y equals to 0 and y equals to 1. So this is y is between 0 and 1. All right. So that will be this yellow region here. That's between y equals to 0 and y equals to 1. Now I'm going to fix my x, right? So if you want to fix your x, so here you have this segment here, right? And you have this point. So this is where y is equal to 0, and at this point here, y coordinate is equal to 1, right? And you want to connect this segment to this point. So first, you're going to use this line, this vertical line. So what's the equation of this vertical line? This is x equal to 0. Okay. So here for x, so you start with a 0, and then we have this circle here, right? In the first quadrant, right? So what's the equation of this this function here, this graph here? Well, it's just it's your circle in the first quadrant. So it's just x squared plus y squared equals to 1 in the first quadrant. So when you solve for x, then x would be positive square root of 1 minus y squared, right? So that would be your, so this is the upper bound, right, for x. So this is square root of positive square root of 1 minus y squared. Okay. Does it make sense to you guys how I got this the new bounds when I changed the order of integration? Is there any question? I know it's sometimes it's kind of confusing, right? But I think the best way to do it is just as I did. You start with like let's say you start with y, so we have to find the constant, the bounds for y, so they should be a constant. So like here in this case for this region, y is between 0 and 1. So then that means I'm going to have this segment here, y equals to 0, and this point here where the y coordinate is equal to 1, right? And then I have to connect them using graph of two functions, right? So I connect first using the x equal to 0, and then I have this graph here. So that's x equal to square root of 1 minus y squared. Anyway, so well, there's no questions, and we can just now change. So I can change the order of integration. So the function again is the same function. We keep the same function, which is 1 minus y squared to the power half, or square root of 1 minus y squared. Now I changed the order for integration, right? So here's my dx and then dy. Okay, so now my x is between 0 and positive square root of 1 minus y squared. And my y is between the two constant 0 and 1. Okay. So now we integrate with respect to x. So if you integrate with respect to x, the 1 minus y squared, etc., it's just a constant. There's no x, so the integral would be the constant times x. So this is 0, 1. So 1 minus y squared to the half times x, right? And x evaluated between 0 and square root of, or just use the same notation here. It's 1 minus y squared to the power half, right? Dy. So we substitute x first with this 1 minus y square 1 minus y squared to the power half. So it's 1 minus y squared to the power half times 1 minus y squared to the power half. All right, minus, and then of course you just substitute x by 0 is going to be just 0. So I'm going to just write it down here very fast. So this is dy. So this is 0. Now we got so 1 minus y squared to the power half, 1 minus y squared to the power half. You add the powers. So when you add the powers, half plus half, that will be 1. So which is a good news, because now it's just 1 minus y squared to the power 1. So it's just 1 minus y squared, right? Dy. You integrate with respect to, you integrate 1. So we integrate with respect to y, of course. You integrate 1, that will be y, minus, you integrate y squared, that will be y cubed over 3, between 0 and 1. You substitute y by 1, you get 1 minus 1/3, minus, and substitute y by 0, you're gonna get just 0, right? So 1 minus 1/3, the answer is 2/3. So yeah, so Zivolod, your answer is correct. I don't know, David, where did you get? I think your answer was, you said for number 1, you said pi over 4 minus 1/3.
Probably miscalculated.
I don't know exactly the answer, the mistake. Sorry.
Yeah, I made a mistake somewhere, maybe.
Yeah. Did you try to use the polar coordinates, or? Because the pi, I think you tried to use the polar coordinates. But anyway, it's not a problem. Okay, so that's for the first one. Any question, guys, about number 1? All right, so now let's move to number 2, which is, I think it's less obvious than number 1.
I just finished calculating it, but I have a really complicated answer.
Okay, it should. I don't think it's gonna be complicated, but let's see. Okay, if it's let's see what happens. I mean, I don't have the answer, guys. I found this exercise somewhere in the textbook, so I don't know exactly what the answer is. But anyway, so let's just do it. So this is 1, 2, 0, and log of x. x minus 1, 1 plus, so it's a square root of 1 plus e to the 2y. I'm gonna just use the power half here instead of the square root symbol, and then of course we have this dy dx. So again, guys, same remarks. I mean, if you try to integrate with respect to y, because of this power, this is square root, and if you try to use the substitution, then you're gonna need, you're gonna need some exponential. So outside this is the square root here. So remarks, first remark. So as I said, if you try to use, if you try to use substitution, then actually, again, we're gonna have a problem, and then there will be a problem. Okay. Again, it's just because, for example, if you say, u is somewhere, that's what I have at the end. Oh, okay, okay. All right, so now let me sketch the let me sketch the region D in this case, right? So we said, so y is, or x first, x is between 1 and 2. So x is between 1 and 2, and then y is between 0 and log of x, right? So y is between 0 and log of x. So I'm going to graph these functions. First, I'm going to graph, so what's x equal to? So here, the first inequality here, x is larger than 1. So let's see what's x equal to 1. Here, I'm going to have x equal to 2. So if you graph x equal to 1 and x equal to 2, so this is, oops. I'm going to use a black here for the x-axis. This is my x-axis. It's my y-axis. All right, I'm going to need, I think, 1 and 2. So here's 1 and 2. So you graph x equal to 1. So here's x equal to 1. All right, and then you graph x equal to 2. So here is x equals to 2. Right. So when you say x between 1 and 2, it's just this region here between these two vertical lines, right? Now, next we have y larger than 0. So y is equal to 0. It's just, again, it's just the x-axis. This is y equal to 0. So you need y to be larger than 0. It means it's going to be above the x-axis, right? This here, above the x-axis. So this is where y is larger than 0. And then next function, it's y equals to log of x, or natural log of x. Okay, so I'm going to graph. I'm going to use the yellow. So if you graph y equals to natural log of x, so net log of or log of x. So log of 1 is going to be 0. So this is, let's say this is log of x. Okay, this is y equals to log of x. So here, for example, this is, so log of 1 is 0, right? Log of 1 is 0. But then log of 2, so this point here, the y coordinate would be log of 2. Right? Now, you need your y to be less than log of x, right? So again, it's just you have this, the graph of log of x, which is this yellow graph, right? So y is less than log of x. So it's either below the graph or above the graph, right? So again, guys, you can just take a random point and check which region corresponds to y less than log of x. For example, you can just take you take this point here, right? Let's take a point 2,0. So x is 2, y is 0. So we're gonna check if y is less than log of x. Well, y is 0. Log of x is 2. Log of 2 or natural log of 2 is just some positive number, and so this is true. Log of 2 is larger than 0. So your region which corresponds to y less than log of x would be the region which contains the point 2, 0. So it's going to be this region here, right? So this is where y is, less than log of x. Does this make sense to you guys? Well, I hope so. Now, if you take the intersection of all these regions, the yellow, the green, and the blue one, then you're gonna get your region D. So that will be this region here, this one here. This is not a straight line, of course. It's supposed to be kind of, it's not a straight line. So this is exactly my region D. Right, that's my region D. Okay, now I'm going to change the order of integration, right? So I have this region D, right? So which is this one here. This is my region D, right? So now, so here, we started with x. We said x is between 1 and 2. And then y is between these two functions, 0 and log of x, right? So now I'm going to start with y. Okay, so what will be the bounds for y in this case? Well, again, you think of y as like between two constants, right? So that will be two horizontal lines. So first you have this line here. This is y equals to 0, right? And in the top here, this point, the y coordinate is equal to y. The y coordinate would be equal to log of 2, right? So this is y equals to log. The y coordinate, right, is equal to log of 2, right? So again, you want to fix y between two constants. So you think of you have like a horizontal lines. So in the bottom we have y equals to 0, and in the top you have this y equals to log of 2, right? So your y is between 0 and log of 2. Now what about x? Well, so I'm going to connect my green segment to the green point in the top. So I'm going to use two graphs. So this one here first, I'm going to use blue, let's say. So this first, so here's, I'm going to try to find the bounds for x, right? So first I have this graph here. What's the equation of this graph? Well, this is supposed to be the y equals to log of x, right? But I need to find the bounds for x, right? So I need to solve for x. So then x would be equal to exponential of y. So here it's e to the y. Okay, so x has to be larger than e to the y and less than this graph here. What's the equation of this graph or this vertical line? This is x equal to, well, here's the point 2, right? This is this line here, right? This is x equal to 2, right? So your x is supposed to be between e to the y and 2. Okay, so the bounds, so if you change the order of integration, you're gonna get, so again, it's x minus 1 plus e to the 2y to the power half, and then dx dy. So y is between the two constant 0 and log of 2, and x is between the functions e to the y and 2. Right. Any question, guys? Okay, no question. Well, so then, okay, so if you get I mean, this is like the half of the answer. I mean, if you get the right bounds, then you're almost done, because that I think in some cases, the problem with the changing the order of integration is to find the bounds, right? Anyway, so now.
Yeah, I've got them wrong a bit. So
yeah. That's the thing. Yeah. But now, does it make sense to you? I mean, how I got the bounds? I mean,
yeah, sure.
Okay, great. So then now I can integrate with respect to x. Well, here there's no problem with the integration with respect to x, because I mean, this is just x minus 1, and everything else. So it's just a constant, right? This whole thing here. This whole thing is just a constant now, right? So it's just, it's just so the integral of this x minus 1, right? So it's x squared over 2 minus 1, integrate at 1, so it's x, right, times my constant. So this is now a constant. All right, so I'm going to keep the constant here. This is e to the 2y power half, and then there's dy, of course, and then your x evaluated between e to the y and 2. All right, so this is 0 and log of 2. You substitute x by 2 first, so that will be 2 squared over 2 minus 2 times this 1 plus e to the 2y, right, to the power half. Right, and then minus, and then you substitute there your x with the e to the y, right? So it's e to the 2y over 2 minus e to the y times 1 plus e to the 2y to the power half. All right. So now, right, so that will be equal to 2. So here's 0 to log of 2. 2 minus 2, that will be 0. And you see here, guys, the magic here, this is 0. So you got rid of this, this 1 plus e to the 2y to the power half. Otherwise, there'll be no way to integrate. I mean, using elementary functions, of course. Right? 2 squared over 2 minus 2, that's just 0. That's very good news, because now we have, so that would be equal to, so here, where is it? So equal to, this is e to the 2y over 2 times the 1 plus e to the 2y to the power half. But this is, actually, it's possible to integrate this, because you see there is this exponential outside. the square root. You see this exponential here? That would be really helpful when you integrate, right? Because you're gonna need it to integrate. Minus, sorry, I forgot there's a minus here. There's this minus here, and then plus. That's e to the y, and this is also another good news because you're going to have this exponential outside the square root, so then you can use the substitution to integrate, right? So this is 1 plus e to 2y to the power half dy. All right, so that will be equal to. And now, guys, I mean, yeah, the computations are not that easy, actually. I mean, in both cases, here, we can use, so here we can use a substitution. This is, right? I mean, derivative of e to the 2y would be just e to the 2y, right? So you can just use substitution u equal to e to the 2y. I mean, of course, du would be, there's this constant 2, of course, right? E to the 2y dy, right? And I got this now, right? This is, I have my e to the 2y now, all right? And here, here you can also use a substitution, right? You can substitution here, right? So let me do first the first one. You can use u equal to u equal to e to the y, right? So then du equal to e to the y dy, right? And I have the e to the y dy, right? So anyway, so in both cases, we can use substitution. That will be no problem. So that's equal to, this is a very nice exercise, actually. It's not an easy one. So anyway, so for the first part of the integral, you substitute e to the 2y by u. So that will be equal to, you know, you're gonna have minus, there is this 1 plus u so there's this 1 plus u, right, to the power half, and then e to the 2y, you know, this e to the 2y, guys, with this dy, of course, there's a dy here, there's a dy here, right? With the dy, that will be du over 2. And then there's a constant 2 here, that will be du over 4. So this is minus du, this is du here over 4, right? Probably I should, probably I should write it in front of here. So again, this is minus 1 plus u to the power half du over 4, and then plus, here the substitution now for the second part would be u equals to e to the y, right? So that would be 1 plus u squared, right, to the power half, of course. And there's this e to the y dy. That's exactly my du. So this is exactly equal to here. This is exactly my du. So let's see. So for the first one here, Did I forget something here? I don't think so, right? So this is for the first integral. We have this 1 plus u to the power half. Over 4. So that will be integral. That will be minus, 1 plus u to the power 3 halves, right? And then you have to divide by this 3 halves, right? So over 2 over 3 here times 4, right? That's for the first part, plus, so this is here, where is it? So this is a square root of 1 plus, I think I forgot u, right? There's u here. Where's u? There's u here, right? There's a u here, sorry. There's a u here. Right? That's correct, right? I mean, let's see. I'm sorry. So what did we have here? There's, yes. Okay. That's u square. Is that correct? No, there's no u, right? So that's e to the 2y. That's the u square. And then, right? And then, where is it? Let's see. Is there? Where's the?
Excuse me, Professor.
Yes.
Why are you dividing by 2/3 and not 3/2?
Did I do? Oh, sorry. That's 3/2, of course. Sorry. I for some reason I tried to reverse the fraction. Yes, thank you. That's of course that's 3/2. Thank you. So here should be 3/2. Right. I mean, of course, here you have to use again substitution, right? I mean, it should be 1 plus u. I mean, it's true. Actually, this is a really long exercise. I mean, to go from this 1 plus u to the power half to this 1 plus u to the 3 halves. Actually, I should instead of well, this is actually substitution here is not really good here. It should be 1 plus e to the 2y. That would be probably easier, right? That's why probably it looks like a very. I mean here. You see what I'm saying, guys? Here substitution. Probably it would be easier if we take 1 plus e to the 2y, right here, instead of e to the 2y. I mean, but in both cases it works, right? Yeah, probably it would be easier to take 1 plus e to the 2y, because to go from this, to go from the 1 plus u to the power half to this 1 plus u to the power 3 half, we have to use a substitution again, right? But then, okay, let's see here. So here I need to use a substitution again. All right. Okay, so that's anyway. So here I'm gonna just keep this. E to the 2y. This e to the 2y here. Okay. I mean, there are different ways. Again, it's either you substitute e to the 2y by u and use another substitution, or just substitute 1 plus e to the 2y. For the second part, we have this. Where is it? Yeah, we have this e to the y times 1 plus e to the 2y to the power half. So here, if you let's say here's I mean, if you say u is equal to the e to the y, then du is e to the y dy. So that will be there's no u here, right? sorry, there's no u here. Should be 1 plus u squared to the power half du. But that's a problem because, we're going to need the u outside, right? So this is not a good substitution here. So probably we should just use, let's see, if you use 1 plus, let me see here. So here we should probably use just, let's see. So it's just u equal to, let's see. So this is a square root. So we're gonna need I'm gonna need e to the y. So u is equal to, oops, sorry guys. Keep the same color here. So let's say u is equal to, so e to the y doesn't work, right? I didn't forget anything because it seems to me it should be e to the y. That's correct. It's x minus 1. That's correct. I didn't forget anything. That's 0. Just make sure that my answers, the steps are correct. That's plus. That's x. All right. And then, oh yeah, probably gonna need integration by parts here. Let's see. So here, if you say e to the 2y, let's say e to the 2y, u is equal to the e to the 2y, then I'm gonna have square root, let's see. I don't want to use the integration by parts. That would be very long, right? So, and I don't think I forget anything here. I don't want to use integration by parts. So I think probably the best thing to do here, let's see. I don't want to use integration by parts. That'll be too much. If let's see. All right, no, probably not that. Let's see. I think probably the best way to do it. I don't. Will be too much. Well, you know what, guys? Probably here we're gonna need integration by parts. That will be like 2 or 3 steps. I'm just thinking about the easiest way to do it here. Will be that would take us like probably 10 minutes at least. Let's see. Did I forget anything here? Let's see. Okay. Probably we're gonna need an integration by parts here, so that would be too much. For we have like 7 minutes, right? All right. What I'm gonna do? Probably I'm gonna leave it. Yeah, for you guys. This would be a really good exercise, actually. Okay, so this is integration by parts. Would be too much. I mean, so probably I'm gonna include the next homework exercise. Next homework. Okay. Anyway, so all right, guys. So as you can see, I mean, well, because I guess I picked this exercise randomly, so I guess that's why it would take too much time actually to do it. Anyway, but that's the idea. You know, you're gonna need the substitution or the integration by parts to compute these integrals, but it's doable, right? Okay, so we have 5 minutes left, guys. So I'm gonna do, well, I'm supposed to start triple integrals, but I guess I don't have time to start the triple integrals. But let me just remind you some what you need to you know, memorize from this section. So so I have a couple of remarks. So first remark is that well, as I said, like for in the homework, like for problem 2 and 3 in the homework, you're gonna use the double integrals to find the area of a region. All right. So just to remind you that, so if you have some region D, so then the area of a region D is just the double integral of, you know, the constant function 1 you know, over this region, over the region D, right? So you have to integrate the function 1 if you want to compute the area of some region, right? The other remark, guys, is that number 2, yeah, so I forgot to include this in the first homework, but I will include it in the next homework. Remember I said that for the analyst, it's not elementary region, but I claim that we can divide it into 4 elementary regions. So, but then you may ask, how can we integrate over this analyst? I mean, if it's not elementary region. But the thing is, so we have this, so D is, you know, again, is just the annulus here, this region here. All right, and we said it's not elementary region, right? D is not an elementary region. Okay, and I claim that we can divide D into 4. So the claim was that so we can divide D into 4 elementary regions. So what will be the elementary regions in this case? Well, actually you can, so the 4 elementary regions would be the following. So we're gonna have first this elementary region here. This is D1. All right, that's my first elementary region. The second elementary region would be the one in the bottom here, D2. This one here. All right, and then the third one is elementary region would be this one, and the fourth elementary region would be this one here. All right, and so what I'm saying is that D1, D2, D3, D4 are actually elementary regions, right? Are elementary regions. So if you have some integral over D, then what you can do is elementary regions. So if you have some integral over D, say you have to integrate some function f of x, y, over D. Okay, then what you can do is you can decompose, this integral into the sum of 4 different integrals. So first over D1, right, plus the integral of f over D2, plus over integral of f over D3, and then over D4. Okay, so what I'm saying, guys, here in this remark is that if your region D is not elementary region, you can try to divide it into elementary regions, and then your integral over D would be the sum of the integrals over your elementary regions. All right. Yeah. So that's what we do when we have a region which is not elementary one. Okay. All right, guys. Sorry, I guess I'm gonna stop here. So next week, I will start the triple integrals. And as I said, so the first homework is on Blackboard now, and it's due for next Thursday. All right. So I'm gonna stop here, guys. Sorry. No, probably I will. I will start the triple integrals next time. Right. We don't have time. Okay. So I will see you next Tuesday, guys. Thank you,
Okay,
everyone.
thank you.
Thank you. Take care.
Goodbye.
Thank you. Have a good weekend.
Bye, Professor.
Goodbye.